Hello everyone, welcome to my YouTube channel. So today I'm going to discuss TIFR GS 2025 MCQ question paper. So sorry for the late video because I got very busy these days. That's why I was not able to make video. So today I'm going to discuss the problems from the MCQ sections because I have already uploaded the video from true false section. Okay, so let's start. So the first question is for a positive integer m, let d of m denote the number of divisors of m including 1 and m, and then we can define a sequence an where an equal to number of divisors of n, okay, such that this is odd. So first you need to find that find the thing is that uh, that an equal to this, right? So how many elements are there such that uh, how many elements m less equal to n is there such that d of m is odd. Okay, so my point is that if you take any natural number and if you ask the question that number of divisors is odd, then you can say something about that natural number. Okay, so what can you say about that? So see, suppose I take some, let's take some example. So let's take 6. What are the divisors? 1, 2, 3 and 6, right? So how do you get these divisors? You are just getting this pair, right? And by just multiplying this pair you will get this exact number. Now if number of divisors is odd, that means there exists some n such that m square is n. In particular, the n must be perfect square. Okay, so if dn is odd, then n must be perfect square. Okay, so then this an is actually root n. Okay, then if you take an by n, this actually root n by n, and that obviously tends to 0 as n tends to infinity. So that's why option A is correct. Okay, so this is a very simple question because you need to understand that you need to know this thing, and this is not very difficult to understand, right? Because the thing that I've already told you, that since it is number of divisors is odd, that means there must be one divisor here such that whose square must be the entire number, right? Or in other words, you can just take the prime factorization n equal to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, and from there you can conclude if the number of divisors is odd, so then what are the number of divisors? This is alpha 1 plus 1, alpha 2 plus 1, dot 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 dot. Okay, so then if number of divisors is odd, that means each and every alpha I must be even, because if alpha is odd, then alpha I plus 1 is even, and so this must be even. So then if each alpha is even, right, so then n must be perfect square, because you can take the take alpha I by 2, so you can take m equal to p1 to the power alpha 1 by 2, p2 to the power alpha 2 by 2, and so on, then m square must be n. This is the exact proof, but so this is a simple thing, so that's why option 1 is correct. Okay, I hope it is clear. Now come to the problem number 2. So S3 be the symmetric group on 3 letters and consider the real vector space V. It is saying that you take set of all functions from S3 to R such that f of g equal to f of g cube for all g. So S3, right, you can write the explicitly the element, right? It is E, that means identity, then you have these 2 cycles, and then you have 2 3 cycles, right? So now observe that g cube, e cube is identity, each 2 cycle has order 2, so that means that cube is the same thing, 1 2 3 cube must be the same thing, and for each 2 cycle you have identity, right? So if this condition satisfied for all g, that means f of e equal to f of 1 2 3 equal to f of 1 3 2. So these 3 things are fixed, but you can define f of 1 comma 2, f of 1 2 this cycle to be anything, because f of 1 comma 2 is same as f of 1 comma 2 whole cube, which is same as f of 1 comma 2, so there is no problem. Similarly f of 1 comma 3, similarly f of 1 2 comma 3. So that means the dimension of this vector space must be 4, because for identity 1 2 3 and 1 3 2, all of the for all these things it is same as where you send the identity element. If where you send the identity element, the condition f of g equal to f of g cube automatically tells you where you need to send f of 1 2 3, right? But for 1 2, I mean for two order element 1 2 1 3 and 2 3, it is independent, the choice is independent. So that's why the dimension is actually 4 dimensional vector space. So it is greater than 3, right? See, so I am making this video, and maybe this video is not very long, because I can't I'm not able to upload each and every problem individual solution, because that will take much time for me. So that's why I'm uploading it. If you have any particular question on any after seeing this solution video, if you have any particular question, then just comment below, I will definitely answer it. Okay, so this is the thing, that this dimension is actually 4 dimensional. Okay, because it only depends on where you send identity, then 1 2 1 3 and 2 3, 4 elements, so that's why it is dimension 4. Okay, so now come to the third question. It is saying that you need to take all pairs such that so 1 second, I want to add some I don't know what is happening, sorry for that. Yeah, okay, so now I'm adding some more page so that I can solve it clearly. So let's take problem number 3. So problem number 3 tells you that you need to take all such order pair in R2 such that equal to y to the power 5 plus 1 to the power 5, if I am not wrong, right? And then you need to find the number of connected components of this, right? Okay, so now if you let's take t equal to this, then what is x equal to t to the power 1 by 3 minus 1 to the power 1 by 3. And what is y? So if t equal to y to the power 5 plus 1 to the power 5, y equal to t to the power 1 by 5 minus 1 whole to the power 1 by 5, right? So then this is what? This is basically take R to R2 f of t equal to this. If you define this map, then this is basically image of this map, right? So S is equal to image of F. Now you can easily see that the component functions are continuous. So F is continuous, right? Because since the component functions are continuous, F is continuous, R is connected. So that means image of connected set must be connected. So this will imply S is connected. Okay, this will imply S is connected. Okay, so that's why number of connected component must be 1. Right. Now come to the problem number 4. That define a set S of real polynomials as follows. That you need to find so all polynomials such that p is not constant and mod of p0 is less than 1, right? And then you have to find up equal to set of all x such that mod px is less than 1. Then what will be this? See, this is polynomial, right? So polynomial functions are continuous, right? Polynomial functions are continuous. So if you need to find all x such that mod px less than 1, then it is basically you need to find p inverse of minus 1 comma 1, right? And since p is continuous, this is open. So that means this is union of open intervals. Now only thing that you need to check, that is whether it is union of finitely many open intervals or infinitely many open intervals, which is not very difficult. Why this is not very difficult? Because if you just draw some picture, then it will be clear, right? This is polynomial function, so this is continuous. If you just draw the graph, then you will get the answer. So what I want to say is that, so let's take the xy plane coordinate. Now you need to find what? You need to find, let's take this is 1, this is minus 1. You need to find, so now draw the picture of, draw the graph of p, and then you have to find set of all x such that the graph is inside this area, right? Right, that's the idea. So now if that's the idea, now you can, now p0 is less than, so p0 is somewhere here. Now if you draw some picture, whatever, wherever is this, so then this can be something like this, whatever it be, can be something like this, right? So but is this possible? That can it go up and down like this for infinitely many times? Is it possible? Not possible, because see, if you take this point, what is this? This is px equal to 1, right? Or if you take this point, this is what? This is px equal to minus 1, right? Now if you have a polynomial, then px equal to 1, px minus 1, or px plus 1, that is also a polynomial, right? And set of all points x such that px equal to 1, or set of all points such that px equal to minus 1, that is basically solution of the polynomial px minus 1 or px plus 1. So that solution is always finite, right? Because this is a polynomial, so number of zeros must be finite. Real polynomial, so number of zeros must be finite, right? So that means this cannot happen infinitely many times. Do you understand? So this thing only can happen finitely many times. So that's why this set is actually open, a union of finitely many open intervals. So now you can understand that why TIFR problems are really interesting and really conceptual. It is not even important that you need to write each and everything very rigorously during the exam, because you have enough time, and if you can think it properly, if you can think in the right direction, then you will get the idea. That's why it is conceptual, and that's why it is very interesting. The problems are very nice. Okay, it's not all the problems are very difficult. Yes, there are problems which are really difficult, but most of the problems are really conceptual, and if you have good idea that how to solve it or how to think properly, then you will be able to solve it. So thinking, they are only checking your thinking ability. Okay, thinking ability. It's not like jam or net or gate exam, like you have to solve a lot of questions within short time and you have to score more. It's not like that. You have enough time, just think it properly and try to figure out the answer. Okay, so that's why for every polynomial, this is actually union of finitely many open intervals, because the px equal to 1 or px equal to minus 1, these has only finitely many solution. Okay, so that's why this cannot happen infinitely many times thing. Okay, so this can only go finitely many times. Okay, so that's why this is finite. Okay, so now problem number 5. This is also a very interesting problem. So observe that it is saying that number of functions r minus 01 to r minus 01 such that f of x minus f of y mod is equal to x minus y mod. So you can easily see that this is basically an isometry. on real number minus 2.0 comma 1, right? This is actually an isometry, so it is basically continuous. It is continuous function. And now if you again, you can just draw graph and you can observe this. So what is happening here? So it is happening here that if x say y greater than x, then either f of y greater than f of x, or f of x greater than f of y, such that the distance is actually same, right? Because this is isometry. But my question is that, is this possible? Like you choose y greater than x greater than z, and f of z greater than f of y, and f of y less than f of x. Is this possible or not? That's my question first. Or in other words, or f of z less than f of y and f of y greater than f of x. You can check anyone for anyone, because other are just reverse. So is this possible or not? That is my first question. Okay, is this possible or not? See, okay, so what I am saying is that, say this is x, this is y, this is z, okay, and this is f of x, this is f of y, this is something f of z. Okay, so is this thing possible or not? Not possible, right? Because in that case, if you take z minus x, this mod, this thing is not true, right? Fz minus fx, this is not equal. Okay, in this case this is not equal, right? So this is not possible. You can easily see that this is not possible, because so that's why if it is increasing, then it has to be increasing, or if it is decreasing, it has to be decreasing. That's the first observation. And from there you can conclude that f of x must be x plus c or minus x plus c. Okay, choice. And then what? Then 0 is not there. So from there, what you can conclude? Obviously f of x equal to x is there. Okay, and then you can check f of x equal to 1 minus x is there. Other parts are not possible. Okay, why not possible? Because if you take c, so if you take f of c, if you take c to be not equal to 0 or 1, constant term is not equal to 0 or 1, then f of minus c, that is 0, right? And minus c is also not equal to 0 and 1, but the isometry is r minus 0 1 to r minus 0 1, right? So that means if you take any element minus c which is not 0 and 1, it has to map to somewhere which is non-zero, not 0 and 1, but here it will go to 0. That's why its constant term cannot be other than 0 and 1, so it has to be 0 or 1. So then 4 cases are possible. So fx equal to x, fx equal to minus x, but that is also not possible because f of minus 1 equal to 1, right? So that is not possible. Then fx equal to x is possible, fx equal to x plus 1, that is also not possible because f of minus 1 is 0, that is not possible. So fx equal to minus x plus 1, that is possible. That is possible. Yeah, so only two things are there. Again, in this problem also, if you draw the picture, if you think it properly, then you will get the answer. So only two. Okay, now come to problem number 6. So problem number 6 is saying that xn equal to 1 minus root n to the power n times e to the power n exponential of n to the power 1 by 4. Again, this thing you need to observe properly. Okay, so what is xn? So xn equal to 1 minus root over 1 n to the power n e to the power, e to the power n to the power 1 by 4. Okay, so then this is same as e to the power n ln 1 minus n plus n to the power 1 by 4, right? So now what is ln 1 minus root over n? If you just use some expansion, Taylor series expansion, then what will you get? This is 2n 1 by 3 n to the power 3 by 2 1 by 4 n square, so on, right? So then n ln 1 minus root over 1 by n plus n to the power 1 by 4, this is same as minus root n minus half minus 1 by 3 root n minus 1 by 4n minus something plus n to the power 1 by 4. Okay. So then this is e to the power n ln 1 minus 1 by root n plus n to the power 1 by 4, which is same as 1 n to the power 1 by 4 e to the power n to the power 1 by 4 by e to the power root n plus half plus 1 by 3 root n plus 1 by 4n plus so on. Okay, yeah, and then you can check easily that this series converges because it is e to the power root n, it is n to the power half, and this is n to the power 1 by 4, so definitely it will converge, summation xn is converge, and obviously this limit tends to 0 sequence because this is n to the power half and this is n to the power 1 by 4, so you can say that the order this goes faster to infinity, right? So that's why 1 by something, this will go to 0. So so that's why you need to just verify this series, convergence of this series, and which is obviously doable. So this series is convergent, that you need to check properly, but I have already told you the idea. Okay, again I am saying that if you have any confusion in any question, then please definitely comment below, or you can just send me an email, I will explain you. Okay, so it is not possible to explain each and everything in details in this video, but I want to give you idea, and I believe that those who are actually going to crack this exam, those who are seriously preparing TIFR exam, after getting some hint, they should be able to answer it completely. Okay, if you need help of solving each and every step, then you won't be able to crack this exam. Ultimately, this video should be helpful. I want to give some idea. Okay, then after that you need to complete the argument very properly. Okay, that's your goal, that's your work. Okay, that's very, very important. Okay, then again question number 7, this is obviously an important problem. If you know some function called Thomai function, I hope everyone knows, and if you know how to at which point this function is continuous, at which point it is discontinuous, if you know this and if you know the argument, then you will be able to solve this problem similarly. Okay, so what about the Thomai function? So in that case, it is basically fx equal to 1 by q when x equal to p by q and 0 otherwise, right, for irrational. And here it is just for dyadic rational number, right, not for every rational but dyadic rational. So similarly, by same argument as this, you can show that f is continuous, f is discontinuous at only these dyadic rationals. Discontinuous. Okay, first of all, at this point it is discontinuous. That is very easy to show. Why? Because for irrational number, f of this is 0, right, and irrational number is dense. So let's fix one point, one dyadic rational number p by 2 to the n, choose a sequence of irrational number that converges to this, then f of xn must go to this, but f of xn is 0 for all n because this is irrational number, right, and this is 1 by 2 power n, which is non-zero. So that's why at this point this must be discontinuous. But the interesting fact is that these are the only points where it is discontinuous. So that means you need to check for other points this is continuous, and for that you need to know the argument that are used to prove that Thomas function is continuous at every irrational number and it is discontinuous only at rational number. Okay, so by using the same argument you can prove here that this is actually discontinuous at only dyadic rationals. Okay, that means p by 2 to the n where p is odd. So that's why option D is wrong. So do you understand that in TIFR problem there are many problems which is actually similar to something known, but you need to understand each and every concept. So most of the students only knows this as an example, but they don't know the actual argument. Okay, but those who actually know the argument or those who understand this properly, they will be able to solve this question number 7 also. That's why being conceptually strong is very, very important for cracking TIFR GS exam. Okay, fine. Now move to problem number 8. Problem number 8 is a very interesting problem, but for that you need to know something related to measure theory. You need to understand some concepts of measure. I mean, measure is not fully used. You need to understand some concept of length of a set of real number or length of something. Okay, so this is mostly for PhD aspirants because they already know this thing. And this question paper is same for integrated PhD and PhD aspirants. So there will be some problems which will be very difficult to solve for IPhD student, but that is not even important because out of 80 if you can score more than 40 then it will be more than enough. But anyway, so for this question you need to understand some concepts of length. Okay, so how to do it? Observe. So x contains all rational numbers because x, this is interval and each interval contains this rational number qn, right? So q is subset of x. So that means q closure must be subset of x closure, and q closure is real number. So this is subset of x closure, so x closure is real number. So x is dense in R. Okay. Now x is equal to R or not. Okay. So x is equal to R or not, or x contains an open interval length 10 or not. For that you need to use the concept of length. Okay, so obviously this length of x is less equal to summation of length of in n greater equal to 1, where in equal to qn minus 1 by n square, qn plus 1 by n square, right? Now what is length of in? This is 2 by n square, right? So length of x is less equal to summation 1 by n square, and summation 1 by n square is convergent and the sum value is pi square by 6, right? So this is 2 into pi square by 6. So this length must be less equal to pi square by 3, right? So that means x cannot be the entire R because the length of the entire real number R is infinite, but length of x is less equal to pi square by 3. Also, x contains an open interval of length 10. If there is an open interval of length 10, say I or say A is an interval of length 10, A is subset of x, so length of x must be greater or equal to 10, right? Because A is contained in this set, so length of A is less equal to length of x. But the definition of length is a property, but pi square 3 is actually less than 10, so this is not possible. Okay, so that's why x is dense in R but not equal to R, and x contains an open interval length, that is also false. So option A is only correct, and x equal to R obviously false. Okay, now question number 9, very simple problem. Okay, how to do it? T is bijective or T is injective or surjective or this. Okay, so this is a linear map, right? So linear map means injectivity. If you want to check injectivity, then what do you need to check? You need to check whether there exists some element which is in the kernel, right? Which is in the kernel or not. So then you can check that, right? How to check? You can just take some polynomial px and you can just check that. So this is, so px is a0 plus a1x plus a2x square. This is very simple one. Right? Then what is t of px? T of px is x times a1 plus 2a2x plus n a n minus 1 x to the n minus 1. So then it is a1x plus 2a2x square plus 1 second. No, it is first you have to multiply this, then you have to take the differentiation. Okay, so first you, so yeah, so it should be t of px should be ddx of a0x plus a1x square, which is same as a0 plus 2a1x plus a2x cube. So that means 3a2x square plus dot 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 n plus 1 an x to the n. So if this is 0, that means a0 equal to 0, a1 equal to 0, a2 equal to 0, and an equal to 0. So that means px is identically 0. So this is injective. Okay. Now what about surjectivity? Surjectivity. If you take 1, so what is basis? Basis is 1x, x square, so on, right? Then if you find the pre-image of these elements, then you will get the entire thing, right? So for surjectivity, if you need 1, so then if you take px equal to 1, then t of 1 equal to 1. Okay. If you take px equal to x by 2, then t of x by 2 equal to x. Right? Then t of x square by 3, that is actually x square, right? And so on. So then t of x to the n by n plus 1, that is x to the n. So every basis element has pre-image, so that means it is surjective actually. So t is bijective. Easiest problem, question number 9. Question number 10. So it's a 3 by 3 matrix. So one approach, obviously you can just directly compute the characteristic polynomial and then you can find the roots, then you will get the eigenvalue, and then you can conclude that what is this or not. And another way that so maybe for 3-degree polynomial it is not always easy to find out the roots, right? And it's not possible to use Cardano's method because that will be very lengthy. You can try. I don't know what will be the polynomial, but I can tell you some easy idea from which you can conclude the answer. So first, obviously observe that A has a positive eigenvalue. That is definitely true. Why? Because if all the eigenvalues are less equal to 0, then the trace must be less equal to 0. But trace is 3. So A has positive eigenvalue. So obviously the first statement is correct. Now 1 to 1. So first row and third row are same. That means determinant is 0. So 0 is an eigenvalue, right? 0 is an eigenvalue, 1 is one positive eigenvalue. Now you cannot say directly whether the other eigenvalue is negative or not, right? For that, what you can do, if you observe, you can directly find the characteristic polynomial, and you can take the what will be the coefficients of this characteristic polynomial based on the eigenvalues. From there you can conclude that A has negative eigenvalue. How? Observe one thing. So suppose other eigenvalue, so alpha is positive eigenvalue, 0 is one eigenvalue and beta is another eigenvalue. Okay, so then x into x minus alpha into x minus beta is there. So x square minus alpha x times x minus beta, which is x cube minus alpha x square minus beta x square, plus alpha beta x. Okay, this is the characteristic polynomial. Now alpha is positive, right? If beta is also positive, then alpha beta must be greater than 0. and if beta is negative, then alpha beta must be less than 0. So then you can just find out the characteristic polynomial and look at the coefficient of x. If coefficient of x is positive, then second option is wrong, other eigenvalue must be positive. And if coefficient of x is negative, then other eigenvalue must be negative. Okay, and you can check that this will be the correct answer. So question number 10 is also easy problem. Now question number 11. So A is a non-zero n cross n real matrix where n greater than 1 and two statements are there. J square equal to 0, then rank of A is less equal to box function n by 2 and rank of A is less equal to then A square is 0. Okay. If you know, if you read basic linear algebra, if you know very basic things about the matrix, then we'll get. Okay. So I hope you know this inequality, right? Because rank of AB equal to less equal to minimum of rank A and rank B and greater equal to rank A plus rank B minus n, where AB belongs to M and R. Right? If you know this, then let's take B equal to A also. Then what will you get? Rank of A square greater equal to 2 times rank A minus n. Now if A square is 0, then rank of A is less equal to n by 2, which is less equal to box n by 2. So this is correct. But if rank of A is less equal to n box n by 2, then A square is 0. This is not obviously correct. Simple example, you can take 3 by 3 matrix and let's take 0. This one. Rank is 1. Obviously this satisfies, but what is A square? A square is same thing, right? Because this is diagonal matrix. So obviously 2 is wrong. So 1 is true, but 2 is false. Okay. Now question number 12. Question number 12 I am not going to explain because this is a very known example. This is called topology sine curve. Okay. And those who have read path connectedness, they will definitely see it. Okay. Whichever book you are reading, you will definitely get it. If you follow my videos already, then I have already suggested you a book for matrix space for preparing NBHM or TIFR, that is Kumar Sen's book, and in Kumar Sen's book this is already given the same example, and it is also proved that S is connected but not path connected. So this is topology sine curve example. So I am not going to explain here, you will get it in the book. It's a standard fact. Now problem number 13. Okay, this is actually a very good problem, and this I don't remember, but this is already a previous year problem of TIFR GS. So if you have already solved some previous year question paper, maybe 2017 or 18 or 19, I am not sure where it was, but it was in some true false section, same kind of problem. So that's why previous year question papers are very important. Okay, but okay, so let's take, so any linear map from R3 to R3 has a one-dimensional invariant subspace. That's the question. So observe that if you have an eigenvalue and if you take some eigenvector and if you take the span of that eigenvector, then that will be definitely a one-dimensional invariant subspace, because T of V equal to lambda V. So if you take the subspace W to be span of V, then T of W must be equal to W, right? Or T of W must be inside a subset of W, right? Subset of W contained in W. So that's why W is an invariant subspace. So of one-dimensional invariant subspace. So if you have an eigenvector, then definitely the span of that eigenvector must be a one-dimensional subspace. So, and now if you have a linear map from R3 to R3, so the characteristic polynomial is a degree 3 polynomial over real number, and we know that any odd degree polynomial must have a real root, right? So that means this linear map must have an eigenvalue, right? And then you can choose the eigenvector and you take that span, then it will have a one-dimensional subspace, invariant subspace. So this is fine. Now So if all three eigenvalues are real, then you can take any two eigenvalue, okay, and you can take any two eigenvalue, and you can take the subspace spanned by the eigenvectors, two eigenvectors, then subspace spanned by any two eigenvectors, then you will get the two-dimensional invariant subspace. But so that means one, this is always true. For second part, it is slightly tricky. So tricky in the sense that if you have two different eigenvectors, then it is fine. You can take the span of that two vectors, and that will be also T invariant subspace. But one thing can happen, that one eigenvalue is real, but other two eigenvalues are complex, right? And so in that case, it is not obvious that why it should have a two-dimensional invariant subspace. But for that, you need to use something. What you need to use? So you need to use a fact, and it's a general fact, not just Rn, okay, not just R3. It's over Rn, or you can say Cn also. This is true. In fact, over any field. But I should not say any field. Let's stick to on Cn or Rn. So, and it's more important for Rn, because over Cn, because over Cn, C is algebraically closed, so polynomial will split. So it's not very important there. Also, it is important because it can have repeated root, but we are not interested there for that. So you will get this theorem in Hofmann-Kunz. Okay. Hofmann-Kunz, you will get this theorem, and this is a very interesting theorem. The theorem is saying that if you have a linear map on a finite dimensional real vector space, let's say V, and if you have and let's P be the minimal polynomial, okay, P be minimal polynomial, and you write P as P1, P2 up to Pk as irreducible factor, okay, irreducible factor, and where this is, so P1 power alpha 1 is possible, P2 power alpha 2 is also possible. So it's, I think it is better to write P1 power alpha 1, P2 power alpha 2, Pk power alpha 2. Okay. Then if you write it, then you can write V as direct sum of W1, direct sum W2 up to Wk, where each Wi is T invariant. Okay. P is the minimal polynomial, mind it, P is the minimal polynomial. Each Wi is T invariant, and if you restrict this T on Wi, then it will give you a linear operator on Wi, and minimal polynomial for that linear operator must be Pi power alpha I. Okay, this is the thing. Okay, so if this is the case, then you can use that here. So we are interested in the case where one eigenvalue is real and other two eigenvalues are complex, right? So in that case, it's polynomial. In that case, the minimal polynomial must be some x minus alpha times some degree 2 polynomial, x square plus alpha x plus ax plus b or something like that, right? And this is the decomposition, this is the factor. So by this theorem, you will get an invariant subspace on which if you restrict it, the minimal polynomial must be this, okay, and the dimension of that that invariant subspace must be 2 here. So any linear map from R3 to R3 must have a two-dimensional invariant subspace. So that's why this theorem is very important. This theorem you will not get it in Friedberg's book. So that's why for TIFR NBHM exam, Hofmann-Kunz book is very, very important, and you need to read this concept. Okay, so if you know this theorem, then it is obvious. Okay, so now problem number 14. Problem number 14 is saying that for a linear operator, for a linear map T from R3 to R3 with a two-dimensional kernel, trace of T is an eigenvalue. So two-dimensional kernel means, what is kernel for a linear operator? It's basically the dimension of the kernel, or you can say the nullity is tells you the geometric multiplicity of the eigenvalue 0, right? So then two-dimensional kernel, so that means GM of 0 equal to 2. Then what will be AM? AM of 0 must be greater or equal to 2, right? So it's R3, so GM of 0 equal to 2, so that means only the trace must be equal to the other eigenvalue, because trace equal to sum of eigenvalues, trace. So trace is lambda plus 0 plus 0, so this is lambda. Okay. So option 1 is correct, because already algebraic multiplicity is at least 2, so 0 will occur at least twice. So that's why the other eigenvalue could be 0. In that case trace is 0, equal to 0, and if other eigenvalue is non-zero, in that case also that eigenvalue must be the trace, because trace is sum of eigenvalues. Okay. And for the second statement, linear R3 two-dimensional current, again x square divides the characteristic polynomial, because algebraic multiplicity is greater or equal to 2, right? So that means x minus 0 square must divide the characteristic polynomial. So x square divides the characteristic polynomial, because algebraic multiplicity is at least 2. This is very simple, basic concept. Second easiest problem after that eigenvalue problem, I think second or third. There are few problems which are very easy. So yeah, so 1 and 2 both are true. Okay, now go to problem number 15. So problem number 15 is saying that, again, I have already told you for NBHM, TIFR, this kind of exam, sequence series of function, this is very important concept, very important concept, even if for interview as well as the GS exam and subjective exam, very important topic, and it's very conceptual topic. So read carefully and understand each and every concepts very well. Pointwise convergence, uniform convergence, properties and all. Read the proofs very carefully, and then you will get it. Okay, then it's very simple. Sin x by n, and then fn prime is what? So fn is sin x by n. So fn x is sin x by n, and fn prime x is 1 by n cos x by n. Right. So now what is fx? Fx is 0, right? And let's take fn x converges to pointwise, gx must be 0, right? For both cases pointwise limit must be 0. So now sup fn x minus fx, this is sup fn x minus 0, this is actually 1, this is sup x by sin x by n, right? So if you take x equal to n pi by 2, then this is 1, so this sup is actually 1, so not equal to 0. So convergence is not uniform. Just definition. Right? But for fn prime, one by n. Right? This is less equal to 1 by n, which tends to 0 as n tends to infinity. Tends to 0 as n tends to infinity. So this convergence is uniform. Just you have to use, and already I think this is very standard example, sin x by n, and it is almost in every book where you have you got this sequence series of function, there you will find this. So I think this is very standard example. So fn prime converges uniformly on R, but fn does not. In fact, this is actually a counter example. In most of the books, I think it is given that it's a counter example where fn prime converges the convergence of fn prime is uniform, but convergence of fn is not uniform. Okay. Okay, question number 16. Okay, question number 16, I am not going to explain it here because everything is given. Okay, so you have a matrix and then you need to do it. Okay, so you can take, so let's take n equal to 2. So 2 by 2 matrix is given. By using that, you can easily discard option B and D. Since it is a MCQ, only one option is correct. And then if you take 3 or 4 and just compute, then you will get that option A is correct. Okay. I don't want to explain it because this is very simple. I mean, statement is given, you know what are the entries, then you have to power the matrix, and powering that matrix is not very difficult because most of the entries are zero. So that's why it is not very difficult to compute the powers of the matrix. Okay, so it's actually easy one. Okay, question number 17, I will explain it in the last because this is a very nice problem and very interesting. I like it. So I'll explain it in at the end. Let me first explain other three problems. Okay, question number 18. Again, this is also a sequence series of functions problem, which is very interesting. So S is a set of functions where the property that Fn converges uniformly to F. Then what can you say about F? Right. So the point is that if you read the theory properly, then there will be counter example and there will be lots of things that if Fn is sequence of continuous function which converges to F, then F must be continuous. This is a standard theorem. So any F must be continuous, but differentiability is not guaranteed. Differentiability is not guaranteed. Okay. In fact, in particular, I don't know whether you know this theorem or not, but this is a very important theorem and most of the years some question is given from that. That is Wester's approximation theorem, right? Then if you have a closed bounded interval AB, then you for any continuous function you can always approximate by a sequence of polynomial function, right? And polynomial functions are infinitely many times differentiable. And let's take some function like mod x. Then there will be a sequence of polynomial functions, so Pn x, which converges uniformly to mod x. But Pn x is infinitely many times differentiable, but mod x is not differentiable. Okay, so that's why option A is correct. Any F must be continuous because uniform limit of a sequence of continuous functions must be continuous. This is a standard theorem. But differentiability is not correct. And in fact, this is the counter example where you can take mod x to be the function and you can take a sequence of polynomial functions which converges to mod x uniformly, but all the polynomial functions are infinitely many times differentiable, but mod x is not even differentiable. Infinite differentiable is very far from that. So that's why the concepts of this kind of concepts are very, very important and you need to know it very clear. So for that you need to read these concepts very carefully from the book. You will get everything. Problem number 19, I am not going to explain it here because this is also a standard fact, you can say, or standard theorem. Okay, so F is continuous if and only if this oscillation is zero. But I will suggest you that you can also prove it by using epsilon delta concept of epsilon delta definition of continuity. You can prove it that if, so what will you prove? If F is continuous, then it is zero. That is not very difficult to prove. Another thing you can prove that if this oscillation is if this is discontinuous, then oscillation must be non-zero. Okay, and that will depend on that epsilon, right? At some point it is discontinuous, that means what will be there? That there will be a epsilon such that for every delta mod fx minus fa is greater or equal to that epsilon for any x inside that delta. By using that you can prove that this oscillation must be non-zero. So this is actually a standard theorem and I think you will get it in some book. I don't know whether it will be there in every book, but you will definitely get it, or you can just search it in Google. I mean, it's a very standard fact. Okay. Now the last problem, question number 20, and then I will come back to question number 17. Question number 20 is saying that number of real cubic polynomials of the form x cube plus ax plus b for each complex roots are on the unit circle. Okay. How many polynomials are there? Okay. So first, this is a real cubic polynomial, so there must be at least one real root, right? Real root, and that root must be on the unit circle. So that means that root is either 1 or minus 1. Real root is 1 or minus 1 because this is on the unit circle. So mod is 1. Okay, and other can be z and z bar, obviously. Okay, so one real root is there and other roots must be z and z bar. Okay, now how to do it? So x minus alpha, x minus beta, x minus gamma. This is x cube plus ax plus b, right? So then x square minus alpha x minus beta x plus alpha beta times x minus gamma. This is equal to x cube plus ax plus b. Then what will be? This is x cube minus alpha plus beta plus gamma times x square plus alpha beta plus beta gamma plus gamma alpha times x minus alpha beta gamma equal to x cube plus ax plus b. Right. So one real root is there, right? So then, since mod of all these things, all the roots are on unit circle, so then this is actually 1, right? So then b equal to 1 or minus 1, the first thing. Okay, so then you have this case 1 is x square plus ax plus b, and case 2 is x square plus ax plus 1, and case 2 is x square plus ax minus 1. Okay, now let's take case 1, x square plus ax plus 1. Now there must be one real root, right? And real root is 1 or minus 1. So then subcase, let's take root is 1, lambda equal to 1. Then 1 plus a plus 1 equal to 0. Then a has to be minus 2. So the polynomial you get is x cube minus 2x plus 1. And subcase 2, say lambda equal to minus 1. Then we will get minus 1 plus a plus 1. This is equal to 0. So a has to be equal to 0. So x cube plus 1. And obviously x cube plus 1 definitely satisfies this condition, right? And again for this case 2, x cube plus ax minus 1. So if lambda equal to 1, 1 plus a minus 1 is 0. So a equal to 0. So x cube minus 1 is a polynomial, and lambda is minus 1. Then minus 1 minus a minus 1 is 0. A equal to minus 2. 2 plus a, a equal to minus 2. So then you have x cube minus 2x minus 1. This is the polynomial, right? But these two polynomial will not satisfy this condition. That why? Because if lambda equal to 1, look at this coefficient, lambda equal to 1. So one root is 1, right? Then if you look at this coefficient, what will you get? Look at these two coefficient. So you will get, say, alpha equal to 1. Okay, alpha equal to 1. Then and beta bar equal to gamma, right? So let's take 1 z and z bar. 1 z and z bar. Then what will you get? You get z plus z bar plus z z bar. That means 1. So z plus z bar plus 1 must be equal to 2 here or minus 2 here. So z plus z bar plus 1 equal to minus 2. And again from this condition, one root is 1, another one is z plus z bar, right? So z plus z bar plus 1 must be equal to 0. So this is not possible. Similarly, this is also not possible. So only two polynomials are x cube plus 1 and x cube minus 1. Okay. So you need to verify all these things case by cases. Okay. Case by cases you need to verify this. Then we will get this answer. Okay. Yeah. So again I want to repeat it small. So b, from the conditions that all the root has norm 1 or on the complex side, so you know that b, norm of b equal to 1. From here and b is a real number, so b is 1 or minus 1. Then you have two subcases, and based on that, and since it is a cubic polynomial, so it must have a real root. So 1 or minus 1 must be a real root, and from there you can conclude that these two are the cases. Okay, so then only two polynomial possible. Okay, so now only one question is left. Let n greater or equal to 1, consider the n cross n matrix. Okay, again. So n greater equal to 1, and consider n cross n real matrices such that trace of ax a such that trace of ax equal to 0 for all x satisfying trace of x equal to 0. Okay. Okay. Then you need to find the properties of A. I have already told you that the fact that in the last previous year question, I have already done a problem on Frobenius inner product. Okay, so on MNR, in particular on MNC, you can define a inner product which is Frobenius inner product. What is this inner product? So inner product of A and B is trace of, on MNR it is B transpose A, and on MNC it is B star A conjugate transpose. Okay, it's the inner product. So here we can define it in this way, that inner product of x comma A transpose is trace of AX, right? So this is 0 whenever trace of x is 0, right? So now let's take W, x inside MNR such that trace of x is 0. This is a subspace, right? What is dimension of W? This is n square minus 1, right? So then what will be dimension of W perp? This dimension must be dimension of MNR minus dimension of W. So this must be 1. W perp has 1 dimensional, right? And okay, and if you take A equal to identity matrix, then trace of identity of x equal to trace of x equal to 0. That means identity matrix is in the orthogonal complement already. Then any matrix, then any A is in the orthogonal complement. This will imply, or I should write, any M in orthogonal complement imply M equal to scalar multiple of identity matrix, because they are linearly dependent, because this W perp is 1 dimensional. So any vector is in W perp must be scalar multiple of identity. And here from this condition A transpose is in W perp. So then A transpose equal to lambda times identity. From there you will get A equal to lambda times identity, which is scalar. And then you are done. Just check. So A is scalar, right? Then you are done. Then trace A whole to the power n. What? Then trace of A must be n times lambda, right? So then trace A whole to the power n is n to the power n times lambda to the power n. This is same as n to the power n times determinant of A, because scalar matrix has determinant lambda power n, where lambda is the scalar, lambda is the scalar. So all the diagonalities are lambda. And for every such matrix, rank of A is also n, because A is non-zero. So A is non-zero, so that means lambda cannot be 0, and in that case, if lambda is non-zero, so then lambda I must have rank n. So A and 2, both A and both 1 and 2 are correct. So these are the entire solutions. Okay, and if you have any question, then definitely ask me. Okay, maybe I'm explaining it very fast, but the main idea of this is that to give you the idea that how to solve these problems. And then if you have any question, then definitely ask me. Okay, thank you.